Hello. This is Module 1.3, Electric Field. This module further discusses how charges interact with one another using their electric fields. This module will complete the picture of electric interactions by weaving the concepts of electric force and electric field together. An electric field is an imaginary field created by a charge. Similar to a gravitational field, it is a long-range force, which means that it can exert a force without physical contact. A positive point charge is one source of electric field. It creates an electric field that points radially outwards. Note that the electric field is a vector field. In this image, for instance, the direction of the electric field vector depends on the position where you are measuring the field. It could be upwards or downwards, or to the left or to the right. Similar to gravitational fields, which is just the force per unit mass, the electric field is defined as force per unit charge. Note that charge is the analog of mass in electricity. We can then write the electric field vector like this. The charge Q prime here is not the source of the electric field, but just a test charge placed in an external field. Similarly, we can write the force exerted by an external field E on a charge Q prime like this. Suppose we place a charge Q prime within the field of charge Q, such as the one shown here. From the second equation, this charge will be pushed by the electric field of charge Q along the direction of the field. On the contrary, if a negative charge is placed in an external electric field, it will be forced to move in the opposite direction. The negative sign reverses the direction of the force, making the force antiparallel to the field vector. A negative point charge, on the other hand, has an electric field that points radially inwards towards the charge. A positive charge Q prime will then move along the direction of the field, causing an attractive interaction. Alternatively, a negative charge Q prime will be forced to move opposite the direction of the field, causing repulsion. The electric field line picture of two positive charges are shown here. Note that the field lines don't connect. A similar thing happens with two negative charges, with the directions of the field lines reversed. These two images shows the repulsive interaction between like charges in terms of electric field lines. An attractive interaction between unlike charges, on the other hand, have these electric field pattern. Notice that the field lines from the positive charge connect with the field lines of the negative charge. So, whenever you see an electric field line, you can imagine it is coming from a positive source and pointing towards a negative source. Let us now technically define the electric field in terms of Coulombs law. Similar to electric force, the electric field is directly proportional to the magnitude of the source charge. It is also inversely proportional to the square of the distance from the source to the point where you want to measure the field. The electric fields at points closer to the charge will then have larger magnitudes as compared to points that are far from the charge. Similar to Coulombs' law for electric force, this equation will only give you the magnitude, which is always a positive value. However, the direction of the electric field is always along the line connecting the source and the field points. If there is more than one source of electric field, such as the one shown here, then the total electric field at a certain point P will be the superposition of all the vector fields. When charges are placed in a conductor, such as the one shown here, these charges will repel each other. This means that they will stay as far away from each other as possible until they reach the surface, where there is nowhere to go. This further implies that any net charge on a conductor will only reside on the surface. Since there are no charges inside the conductor, then the electric field inside will also be zero. You can also think of this as the electric fields of the charges inside are canceling each other out. However, the electric field outside a conductor is not necessarily zero. Let's now have an example. Suppose we have a positive 1 nanocoulomb point charge located at the origin. We are then asked to find the magnitude and direction of the electric fields at point P1, which is located at x equals 2 meters, and at point P2, which is located in quadrant 1. For the electric field at P1, which is E1, the direction of the field is to the right or towards the positive x-axis. Knowing the direction, we solve for its magnitude using Coulombs law. Substituting the given values of Q and R1, we get a value of 2.25 newtons per coulomb. The magnitude and direction of the electric field at P1 is then 2.25 newtons per coulomb to the right. In terms of vectors, it is 2.25 newtons per coulomb I hat. For the second problem, the electric field at P2, which is E2, is pointing in quadrant 1. This means that it will both have positive x and y components. By looking at the geometry and the location of P2, the direction of the field vector is 45 degrees. Knowing the direction, we are left to solve for the magnitude. But before we can do this, we still need to solve for R2, the distance from the charge to the point P2. Using trigonometry and the Pythagorean theorem, we find the value of R2 squared to be 2 meters squared. Note that we don't need to solve for R2 since what we really need is R2 squared. We then use Coulombs law and substitute the given values to get a magnitude of 4.5 newtons per coulomb. And that's it. We have solved the problem. If you are still interested in what the vector form of these results looks like, then we can solve for the components of E2. Knowing the magnitude and direction theta, we can solve for the x component using cosine law. We then get a value of 3.18 newtons per coulomb for E2x. Similarly, for the y component, E2y, we use the sine law to get 3.18 newtons per coulomb. Note that the values for the x and y components are the same since the angle is 45 degrees. We then have the vector form of E2. Let's now have a situation where there is more than one source of electric field, that is, there is more than one charge. In this example, we have three charges. Q1 is a positive charge located at the origin, Q2 is a negative charge located at the y-axis, and Q3 is another negative charge located at the x-axis. We are then asked to find the magnitude and direction of the total electric field at point P, which has coordinates x equals 2 meters and y equals 2 meters. To solve this problem, we use the principle of superposition of electric fields. At point P, the electric field due to Q1 will be pointing away from Q1 since it's a positive charge. This vector, E1, will be pointing in quadrant 1, which means it has both positive x and y components. The electric field due to Q2, which is E2, will be directed towards Q2 since it's negative. Lastly, the electric field due to Q3, which we will tag as E3, will be pointing downwards. The total electric field at point P will then be the vector sum of all the three electric field vectors. In terms of components, the total field will look like these. Note that E2 has a direction of negative I hat, while E3 has a direction of negative j hat. If you look closely, we only need to find four terms to solve this problem: E1x, E1y, E2, and E3. Let's first start by calculating the magnitude of E1. Similar to the previous problem, the direction, or angle of E1, which is theta 1, is still 45 degrees. We then solve for R1 squared to obtain 8 square meters. We then use these values to solve for the magnitude of E1 using Coulombs law for electric field and get a value of 1.125 newtons per coulomb. We can then use cosine and sine laws to solve for the x and y components, respectively. So, we have now solved the first two unknowns. For the magnitude of E2, we again use Coulombs law. Knowing the charge and our values, we get a magnitude of 2.25 newtons per coulomb. We do the same for E3 and obtain a similar value. Note that Q2 and Q3 will have the same field magnitude at point P since they have the same charge values and are both equidistant to point P. Now knowing the four unknowns, we can then proceed to evaluate the total electric field vector. Substituting all the values that we have obtained to the original equation, we get the component form of the total electric field vector. Note that this vector has both negative x and y components, which means that it will be pointing in quadrant 3. However, this is not the end of this problem. The problem requires us to get the magnitude and direction of the total field vector. To solve for the magnitude, we again use the Pythagorean theorem to obtain a magnitude of 2.06 newtons per coulomb. In solving the direction or angle theta of the total electric field vector, we will again use the inverse tangent formula. However, we should be careful when using this, especially that our vector is pointing in quadrant 3. In general, when a vector is pointing in quadrant 2 or 3, the inverse tangent formula in your calculator will not give you the correct answer. Instead, you need to find the second angle by adding 180 degrees to the value given by your calculator. Note that there are always two angles with the same cosine, sine, and tangent. For this problem, the correct angle will then be 225 degrees. Now, what if I place a negative charge Q4 at the location of point P, and ask you to find the total force on Q4 due to the other three charges? How will you do it? Of course, you can use the method discussed in the previous module where you take the vector sum of all the forces acted by the other charges. However, there is an easier way now that we know the total electric field at point P, and that is by taking advantage of the relationship between electric force and electric field. The total electric force on Q4 will then be the product of Q4 and the electric field at the location of Q4, which is just the total field at that point. Since Q4 is negative, it will then move in the direction opposite the total electric field. Using the given value of Q4 and the previously obtained value of E total, we then get the component form of the total force vector. We again use the Pythagorean theorem to solve for the magnitude. However, we can also use the magnitude of E total to solve for the magnitude of the total force vector, and we still get the same result. For the direction, we can use the inverse tangent formula and use the value given by your calculator, which is 45 degrees. Note that the anti-parallel direction of 225 degrees is 45 degrees, and both these two angles have the same tangent. Try to verify these results using the method discussed in the previous module.